Yes, thanks for inviting me to this seminar series. And today I was planning to first give a very brief overview of our new VILMA Center of Excellence. So what are we doing? What are our objectives? And then so what I'm doing there is machine learning. So then I will explain some of the machine learning problems that are relevant for this virtual laboratory, at least from my viewpoint. And finally, I will present our recently accepted journal paper, SLISEMAP, which is a tool for explainable AI that we will are planning to use in this virtual laboratory. So this is the plan. Okay. First, what is VILMA Center of Excellence? So it is a Center of Excellence in the Academy of Finland Center of Excellence program, and these are large projects for the duration of 8 years. And we are quite a few people, as you can see from this slide. So I'm here, so this color coding is for the specialty. So particular intelligence is pink, so whatever is the color. Theory and modeling is theory and modeling in chemistry, physics, so it's in green, and experimental people are in blue. So there is a bit dark division, but what you see that we are people from AI and machine learning, and also from theory and measurement, the theory of atmospheric sciences, and also the measurement devices, and also we are also from different institutions, also Finland and Tampere and University of Helsinki, of course.
Hi, why is there a question mark by Patrick? A question?
Yes, so this is all the logo is randomly. It's a quotation mark, this plug here is a question mark. We don't really know what we are doing. So but it has been very unfortunate of getting the question mark. So it's a visual style, so it's not personal. So Patrick, of course, knows what he's doing to clarify and to avoid any discussions afterwards. Okay, so what is now the, let's say, the physics or chemistry atmospheric science problem that we are tackling? We want to briefly understand from, let's say, theoretical first principles levels how new particles form in the atmosphere. And this is related to one of the, let's say, major contributions of the University of Helsinki in the fields of atmospheric sciences. So it might be a bit surprising, but roughly half of the small particles or aerosols in the atmosphere, so they start from gases. So they are not starting from dust or anything like that, but they start actually from the gases. And it essentially means that you have a very small, small molecules, and then small fraction of them start colliding and attacking to each other, and if everything goes very well or very badly, so then they will form larger particles. And then these larger particles, so what is now the significance, practical significance of these particles? So there are several. So one is, of course, air quality. So these particles, they are one of the major health problems according to WHO in the world, and so understanding this problem enables us to, let's say, understand air quality better, and maybe also solve this problem to some extent. And also in climate models, so the role of the particles is that they get sunlight, and because this particle formation process is not perfectly understood, so this is actually one big uncertainties in climate modeling. But maybe for us, as a center of excellence, let's say the main motivation is to understand, let's say, the quantum chemistry and measurement devices, what goes into there, and the side products, of course, we then have these significant societal impacts outside our laboratory. Okay. So we have two challenges. We have more challenges, but we have split them into two challenges. So first challenge is that when we start from these very small small things and small things. So then we can, in principle, we can by physics and chemistry simulations simulate how these molecules behave, and then we can compute how these form into larger particles. But in practice, we can't do this in the lifetime of the universe. So this is one very big problem that what you can see here. So see here is a kind of a picture, and I hope nobody asks me anything about the picture because I can fake for a time that I understand it, but I mean I really am not expert in this topic. Ask about machine learning. So essentially these solid curves are theoretical predictions, and it has taken several years, I think, and years, Volko's time years to compute these curves. And then they have a reasonable match to the experiments, but by this quantum chemistry computation, we have no hope of covering all the relevant compounds that are flying around in the atmosphere, and all possible reaction chains, and we are very far in very astronomical numbers. So this is one thing, that even small elements take lots of time to compute by using these physics simulators. And then the second problem is that the measurement of these particles is also difficult. So we can measure very big particles, but especially when we go to small particles, then the measurements get more difficult, because when you measure molecules, you must charge them and you disturb the process, and then it's actually a gap. We can simulate small molecules, and then we don't know anything, and then we can measure a bit bigger molecules. And we want to close this gap from both sides, better simulations and better measurements. And then for the measurements, I mean, of course, this is also one thing that I will not talk about, but we hope that we can use machine learning and probabilistic modeling, for example, to model the measurement devices. So these are now the two kind of challenges that we are tackling here. Okay. And the machine learning relevant to us, or relevant to me. There are also some other machine learning that we are doing that I will not cover here, but I will maybe just briefly mention about it. And here you can see the AI mascot with a pink shirt. And in the finally, I will ask you what is the difference between the mascots I have shown, so you can try to spot the differences between different mascots for different slides. Okay, so what is now the virtual laboratory? So now the idea in the virtual laboratory is that we have some physical or chemical or atmospheric or whatever process that happens in the real world. So in this case, some molecules get together and start forming particles. And then we have measurement devices, which in our case are often mass spectrometers that try to measure this thing, and then finally maybe these particles from clouds, or they get in somebody's lungs or something quite nice. So we have a real world process, and then in order to somehow computationally model it, we make a digital twin of this process. So we simulate this formation of these molecules, and we simulate the measurement devices and so forth. And so it's kind of one of the essential ideas that we want to make a twin of this process. Of course, initially this twin might be just few simulations and few measurement devices, but this is something that we hope to expand. And then what is the virtual laboratory? So the virtual laboratory are then, let's say, the tools and microscopes that we can use to let's say, measure things in the digital twin. And equally that we need mass spectrometers to measure things in the real world or microscopes. So in digital twin, then what we need is explainable AI. So how can we, because now these digital twins, so they contain some machine learning elements. For example, to replace these very hard, expensive to run quantum chemical simulations, we essentially use regression models. So then we want to understand how these regression models work, what are the relations that they incorporate. And the second question is that how do we want to build and explore the models, so interactive model building. And then important topic is also the big one here, uncertainty quantification. So can we trust our predictions? So now imagine that we make this regression models is somehow this molecules and then we want to of course apply it to new molecules, and then the question is that what are the confidence limits? And then it turns out that especially when we are dealing with computing confidence limits, is always difficult, but especially when we are dealing with machine learning models which have lots of assumptions, and for them, I mean, quantifying this confidence or uncertainty is in no way trivial thing. So these are the three things that I'm kind of interested myself and my colleague Martin Rinke, the additional interest of active learning. And active learning comes into play in a context that when we are trying to train these regression models, we have to have, of course, some data to train, and to get the data to train, we have to run some simulations which are expensive, or do some experiments which are equally expensive. So then the question is that what types of how to pick the training data, how to pick the molecules that we simulate. So this is active learning problem. And then finally, for example, studying how to model these measurement devices using, for example, the AFM methodology. Hopefully, I will be doing that also in some point in the future. So this is now the, let's say, the AI that we are doing or concentrating. So then I will now then go through these items, give some examples, and of the last item is level AI. So I will then talk a bit more in detail. So first, can we trust our predictions? So the main question here is that if we train our machine learning models, which in our case are typically regression models or something similar, so how can we then know if we can trust the predictions of the model when we apply them to new data? And one topic here is concept risk, that how robust are we against the concept risk, and how we can quantify that. But I will not now talk about that more today. And then the second topic is interaction, or how to interact with the user. And so we would like that somebody would use our methods. And for some reason, these atmospheric scientists, they don't like installing Python libraries and things like that. I don't know if you have noticed, but then to that end, we have made, for example, this is one quite nice example of what we have done. I think that we have built a tool that uses, for example, web assembly that is such that I mean, essentially what we can send some person like for example, just a link, and then his browser loads the Python and everything, so he doesn't need to install Python or any libraries, but everything is running inside the browser. So essentially, how we deal with these people that we don't ask them to install anything, but just give them a link, and then they can use our applications in the web browser. And this is, I mean, one important thing. And hopefully, in this virtual laboratory, so this will be one important component of that in some form, I think. And you can actually try this assembly version in these links, and you can run our application in your web browser. Yes. Okay. So that was these two first things, and then the third thing, which is kind of the let's say the technical part of the talk, because for some reason, I mean, I think it's nice to have a technical part of the talk. I don't know if it's really useful, but so one big topic that I have been working lately on is, or actually for, let's say, like 10 years, is explainable AI, and the kind of the motivation behind explainable AI is that machine learning models, so they are nowadays very powerful in the sense that they are very complex. They can find very complex relations, and then they can make very accurate predictions. But then there are several, of course, drawbacks for this. So one thing is this uncertainty quantification it's very difficult. And the second thing is that it's very difficult to understand what these things are doing. And in many cases, it would be very useful to understand, especially if we are doing science and we would like to understand things that, okay, the prediction is not enough. So we also want to understand that why we get this particular particle formation rate of our AI algorithm, for example. Or if you are in some other field, like in a bank, so if you use machine learning for credit, deciding whether you give somebody a loan or not, so then you have to quite legally be able to explain why you refused a loan, for example. So it's kind of the same thing. And so this brings us to explainable AI. So what I'm describing here is SLISEMAP, which is a tool that provides global explanation and manifold visualization. It will be part of the Anton Björk's PhD thesis. Okay, and so now I don't know if you know about explainable AI. Probably most of you know. Most of you don't. Good. Know that. So this is a very crash intro. Please read some good book if you want to know more. So the idea is that we have a black box classifier. I think this is a regression model or classification model, and it's so complex that you can't understand it because of your cognitive limitations. And then one way is to somehow make a simpler classifier or regression model that somehow approximates very well with the complex model, and this you can explain. So maybe it doesn't capture all the details, but maybe it will give you the big picture. And these are called global explanations. It is very nice, but what's the obvious drawback? Well, the obvious drawback is that if you have a complex model, so I mean there is no single explanation. So this is why what people are mostly working now currently is that they don't even try to explain the whole model, but they just want to explain why model works for a very big data item. So if you are classifying cats and dogs, or it might say that, okay, this image was classified as a cat because it has these nice whiskers, for example. So the explanation is local with this one image or one instance, and then you give a local expressible explanation, and the user somehow is supposed to understand it and be happy about that. So there are, I mean, two points. We have this black box model, which is very complex, difficult to understand, and then we have a white box model, which is, I mean, easy to understand and somehow explains the user how the black box model works in the vicinity of this interesting point. These are called local explanations, and I have some examples of that later. Right. Okay. And then this is a kind of a technical point, but it's not, I mean, maybe that technical. So now if we go to, let's say, in a way, still a bit deeper in a sense that assume that we have a classification problem, that we have two parameters x1 and x2, and then we have classes plus and minus, which are now shown in this figure here. I show figure here, and you notice that the data is, or the x2 is constant. And then when you train a classifier, for example, so then of course the classifier will classify this kind of function that if you give it a point, so it outputs a plus. And of course the classifier will always output something also for, let's say, for the values for which there is no data. For example, here in this example, the classification boundary is shaped such that if we want to explain it one certain point, so typically how these state-of-the-art methods work is that they sample data points around the point of interest, and then they notice that, okay, the classification changes most in this case the direction of the x2. And then it would say that, okay, x2 is now the important variable for classification, and it would now be the explanation. But this of course goes wrong in a sense that the data, there is no data with that direction. So in a way, this explanation is inconsistent with the data. And kind of the underlying problem here is that in order to define a neighborhood, you have to define a distance. And defining a distance in a data space is very difficult. So, for example, how do you define a distance between two natural images? And or then how do you kind of define distance between two physical systems? So, and how do you take into account all that constraints? But like in physical systems, we have all kinds of physical conservation laws and different things that we know that the data is typically in a, let's say, in a subspace or in a submanifold, so to speak. And this is something that is very difficult to quantify. This is also one thing that the current or previous estimation method struggle with. And we claim that so a couple of years back, so we made a local explanation method for SLISE that did away with this problem that they didn't, let's say, sample. We didn't want to sample new data points because they might lead to nonsense explanations, but instead we used, let's say, existing data points. So and we formulated this explanation problem in the form of the robust regression. So in this image, what you can see here is that this x is now we have only one variable here, and this x is now the function that we try to explain. And then if we want to explain this point that is shown with orange, so then we hit a straight line, and this straight line is now understandable model, such that it contains maximal number of points which are close to this line, and the other points are outliers. So this, if you know what is robust regression, so this is in a way one form of the robust regression. So essentially, we did away with this non-physical points by formulating the exploration problem in the terms of the robust regression. And this requires some effort because normal robust regression methods will break down if you try to do this, but our method actually works also in this kind of case because most of the data points are now typically outliers. So this was motivation one. So local explanation. So we want to have local explanations that satisfy physical constraints or don't lead to nonsense explanations. And the second motivation is that now the separate thing. So SLISEMAP was local explanation plus manifold visualization. And the idea in the manifold visualization is that we have some distance measure in some space. Like here we have a distance measure of different genes, fewer genes, for example. And it's also actually also there it's very difficult to construct this distance measure, but people have done that. And then you compress the data into two dimensions, typically such that the neighborhood relations tell you something of the distance between the original space. And if you do that, so then, for example, in this example, you can find some functionally relevant areas of genes. And this is one of the main tools in genetics, for example, what people are doing. That they use the reduction method and then they see something that is quite useful. And now we want to somehow visualize this, bring this to atmospheric sciences or our virtual laboratory, these types of methods. And okay, and then so these are now the two main ideas. And then on the slide that is just that we combine the reduction and local expectations in a smartish way. And the idea here is that we want to find an embedding of the data points to the two dimensions typically, such that if the data points are nearby in the embedding, so their project is nearby, so they have a similar local explanation. So it's actually, if you understand what is embedding and what is local explanation, so it's actually quite a simple idea. And now the good thing is that we don't actually need a distance measure between the data points to do this. So we are kind of doing away with need to sample new data points thing or need to define a distance, which we can't do very well. So this is only one added advantage because we are using essentially a robust regression. And this is my only slide with some formulas. I also understood that in computer science talks you also always have a slide with formulas. And this is the problem definition. So we have only one we have a black box model. So this might be some regression model, for example, that we try. Like for some function or classification model with output probabilities. And then we have a radius. So the radius is actually the only parameter of the model. So it's a real number. So you can think it's 3.5, for example. And then we have some data points which are typically real vectors in our examples, but in principle they could be something else also that very better. And then we want to take these data points and project them into 2 dimensions. So typically, I mean, we will also use other dimensions, but that's in 2 dimensions. Such that, and we for each data point, so we have the embedding in 2 dimensions. And we also have white box model, which you can think is a linear regression model if we have a linear regression, or multinomial logistic regression if we have classification. But you can think that okay, these white box models G are just linear models. And when we have done that, so then we can write down the loss function, where this L is, if it's linear regression, it is just a quadratic loss function. And now if you look at this formula, and then you might notice that this is essentially we have lots of weighted linear regressors here, and we sum their losses together. So it's anyway, and then we weight is defined by the embedding. So if we have an embedding and we have a distance of less than 1 between 2 points, so they are modeled essentially by the same regression. But if they are further away than or big than distance of 1 or much further away, so then they are independent. So essentially, if we know the embedding, we can compute the weights, and then we have just n linear regression fits, which is quite simple to do. And then we have a constraint that we want that the average distance of these embedding points is this radius. And when we and this is now something that we can do, so we are using PyTorch because it has lots of numbers, so it's better to use GPU, but in principle it's something doable, and we also have some other heuristics. And now the idea is that if on the right hand side, on the top, we have the image where we have model that can be approximated by 2 straight lines. So the line that embedding of this would be 2, let's say 2 clusters, one for blue spheres and one for orange crosses. And so now it says that okay, the explanation for this blue point is the straight line that goes up, and the explanation of the orange point straight line that goes down. And this is now the I mean the idea. So we input the data point and the radius, and outcomes is embedded. If it stops, usually it stops. But maybe it always stops, but I mean it's also more about this maybe running time later. And here is an example of a bit more realistic data set, not super realistic. So this is the random forest. We have used random forest classified the cast data set, and cast data set is one of the classic machine learning data sets that which people use to get a grant of the algorithm. So this is data set of different casts, and the regression target is miles per gallons of fuel consumption. So higher miles per gallon is less fuel consumption. And we notice that okay, the SLISEMAP have clustered the cars into something like 5 clusters. And if we look, for example, now this blue cluster, so we have this very interesting visualization here that now shows the regression coefficients of the simple white box models that approximately this random forest models. And then we notice that these blue points, for example, they have in the year is bigger, so the miles per gallon is bigger. And these are the Japanese cars that due to competition, so their fuel consumption went down as the years progressed because of the high competition. And then these red points, for example, so these are heavy American cars. So they behave a bit differently. and so forth. And now in the virtual laboratory, our idea is, of course, to apply this to molecules, and we get out functional groups of molecules, for example. But maybe a bit more about that later. And okay, some technical things then about the parameters. So we have the one parameter called radius, and if the radius goes to 0, so everything compresses to 1 point, and then we try to model all the data by one linear model typically. And it would have a low fidelity but very high consistency, I mean properties. So we have two measures, fidelity, so how well we match the black hole and consistency, so how robust we are with respect to changing of the targets. So and that is the radius goes to infinity, so then everything goes very far away, and all points are put by the individual nodes, so then we are always with. And for our data set, radius of like 3.5 square. So typically in machine learning, you always have this between is good compromise. But this is really only the parameter here. And then one interesting property of the slide that is that, and this is also a property of all the explanations, of many explanations, that often the explanation is not unique. Especially if we have only one target variable, we have like regression with for one real number. So it might be that some data point would be explained roughly equally good by several local models. And this is, I think, something that people I guess that if you are doing explanations just for one point, so you might not notice it, but if you are doing it for global explanations like we are doing here, so then you kind of notice it. Yeah, and then it's running time, and so this is this file that contains lots of numbers, like numbers, which means that it's a very large data set, so we are in trouble. But luckily, one way to make embedding even for very large data sets is to train this embedding in a subsample of the training data, for example, and then we can check find the embedding, and then we can just add code to the embedding. So this is a way to scale SLISEMAP to very large, like data sets of millions of points. And as I said, so we are using PyTorch, which comes with the automatic GPU acceleration if that, and so it's really helpful for larger data sets. And okay, and then the usage, so it's actually quite straightforward to use. So you install SLISEMAP, and then you can run these all the examples with few commands. So essentially you can define something, optimize it, and then you take a plot. And you can find from our GitHub page notebooks, which we need tutorials for if you get started with anything. And I think really, I mean, easy that because it takes in as a CSV file, so it's it could be quite straightforward to run. And it's licensed under MIT license, so it's open source. Okay, and the summarizing. So I tried to give you an overview of what we are planning to do with our virtual laboratory and what it is, and then some of our recent work, and especially I presented a slide in which we try to combine manifold visualization and global explanations to form actually a global explanation of the machine learning model and also the underlying data. And it turns out actually to work quite nicely, and the explanation method performs comparably, or sometimes even better than let's say the current state of the art global explanation methods. And then actually here in the XIPLOT example, you can see visualization of some of our molecular data sets, just to show that it actually will also work in the virtual laboratory, but this is still very much work in progress. Okay, I thank you for your time.
Thank you a lot. So are there questions for Kai? Yes, Adam?
Yeah, it's really interesting. So you take this kind of two nice methods of linear regression, dimensionality reduction, is defined as good. One question I had was in the dimensionality reduction side of things. Like when you increase this radius to infinity, was it that like by doing so you have to use then like each point becomes its own cluster?
Yes,
And then how does that work? By like you apply a linear regressor to each point individually, or
yeah.
do you need an infinite then number of linear regressors? Or
No. So all the parameters I have is that I have linear group for each point. So this is constant. And then I didn't show you, but we have a small lasso regression there also. That's what problem exception. But essentially, you get the same as you get by one point, which doesn't make much sense.
Yeah. And then the other thing was by kind of like in this case, it's not arbitrarily splitting the data into different groups. It's not arbitrary by any means, but it's with this kind of dimensionality reduction technique. But do you think that this can also help to show that maybe because you're using linear regression, but this could in some cases show second order correlation with parameters by splitting up the data set into different groups? Like because with linear regression, typically you want like you cannot use correlated parameters in your linear regressor. So, but by separating different data points into different groups, you think you're able to recover some kind of like second order correlations and use the linear regressor because of that, or?
Yeah, so
like if all of your predictor of your X variables are not linearly independent.
Yeah.
Like by separating the data, are you able to then say that like now we can use a linear regressor because we split these into different things, or?
Yeah, so I don't think exactly now. I don't have an intuition if but essentially what we do is that we do kind of piecewise somehow make this data in piecewise linear areas.
Okay.
And also whatever kind of correlation you have, so if you go to small enough scale, you can always make a piecewise representation. But it's not kind of clear that if you would have this linear correlation, this kind of correlation structure, so how would it show up? Yeah, so it would show up somehow.
I would be interested to see because I mean, like my real world cases, we never have completely independent parameters, right? So then it's kind of throws linear regression out of the box, like just cannot use it efficiently. So, but I would be interested in seeing how this type of approach works when you have cross-correlated parameters in your set of X variables.
Also probability scale, of course, like it simple could be something else than linear.
Right.
Now, because this was the choice. The second thing is that I guess typically these type of things, these are iterative processes that I mean, you see something and then it's often an objective for further study. So anyway, wouldn't probably give you the final answer. So maybe that would help you to discover these correlations, for example.
Yeah, because I had tried something just some months ago about what about clustering it and then applying linear regressors, but then it's still problem of the cross-correlated parameters wasn't sure how to solve it. But this could be something interesting. Thanks.
Other questions? Okay, so in this case, thanks again.